So you are welcome. Our discussion is on electric field lines and strength. When we talk about electric field is the region of space that is around a charged object. So we take a charge and there's a certain region of space or a certain distance around the charged object that has some field strength, that has some force. So that area or that region of space is called electric field. This region of space tends to exert electric force on any charged object which finds its way in the field. So if any object is found in that space, the charge exerts some force which is electric force on that charged object found in the field. Then the electric field created by positive charges have the field lines pointing outwards. So as shown in the figure, we see that positive charges have field lines which are pointing outwards, and negative charges have field lines which are pointing inwards. So we note the difference between the direction of the field lines for both positive and negative charges. For positive charges, they have their field lines pointing out of the charge, and negative charges have their field lines pointing inwards or into the charge. Now, if a test charge is brought into the electric field, an electric force will be exerted on it. When we talk about a test charge, it is a small positive charge which we use to test the range at which we can feel the electric field force of a charge. So we use test charge to test for that. Now, to be able to determine the electric field, the electric force exerted on the test charge is divided by the magnitude of the force. Now we want to know the electric field of that charge for us to determine that the exerted force on the charge is divided by the magnitude of the charge for us to get the electric field. So mathematically, the equation is giving us electric field equals force over test charge, which is E equals F over Q naught. So we should note that our Q naught is the test charge. And I said earlier on that test charge is a positive small charge that we use to check the electric field of a charge. So as shown in the diagram below, when we have a charge which is positive and we want to know the range at which we can feel the electric force of the field of this charge, a test charge is introduced in the field and we know the amount of force that will be exerted on the charge. So here's our test charge, here's the charge, and here's the direction of the electric field and the force being exerted on the test charge. So now we know electric force equals Q1 Q2 over R squared. We know that electric force equals Q1 Q2 over R squared. But with this, our Q2 here becomes the test charge, which is Q naught. So substituting that into the equation, we're having F equals Q1 Q naught over R squared. So we know that Q1 Q naught over R squared. So we bring back the electric field equation, then we substitute force into that equation. We are getting E equals the force component, which is Q1 Q naught over R squared, all over the test charge in the electric field. So this is how the substitution will be done. So after simplifying the equation, we are getting E equals Q1 over R squared. We are getting E equals Q1 over R squared. So this is the equation to calculate the electric field of a charge at a distance P from the charge. Now, looking at this diagram, we can see two different charges, which is positive and negative, and a test charge being introduced into the electric field. Now, I said earlier on that the field lines of positive charges are pointing outwards. So when we introduce the test charge into the field of the positive charge, the direction of the field will be the same as the direction of the force applied on the test charge. And for the negative charge, the direction of the electric field will be opposite to the force or the direction of the force on the test charge. So you are supposed to note the difference. When the electric field is known, we can determine the electric force with F equals Q times E. So when we are given the electric field, we can therefore calculate the electric force given the charge that is exerting the field. So in this equation, we have two charges being placed in the field. So we have the first one, which is a positive charge, which is aligned in the direction of the electric field, and the negative charge, which is aligned opposite to the direction of the electric field. Now the direction of the force depends on the sign of the charge. So if the charge is positive and it is found in a positive field, the exerted force on the charge will be in the same direction as the field. So a positive charge found in a positive field will have its force direction same as the direction of the field. And if the charge is negative, the direction of the force will be opposite to the direction of the field. Now let's look at some worked examples. So the example here states a point charge 5 microcoulomb is placed in free space. Calculate the electric field at a distance of 0.42 meters from the charge. So we have to find the electric field given some distance and a charge. So into our solution, we first state the equation of the electric field, which is K Q1 over R squared. So E equals K Q1 over R squared. Now we state out our parameters given in the equation. Our Q is 5 microcoulomb and our R is 0.42 meters, and we know our K constant to be 8.99 times 10 to the power 9. Now we substitute these values into the equation and we are getting E equals 8.99 times 10 to the power 9 multiplying the fraction 5 times 10 to the power minus 6 all over 0.42 squared. So after computing this value, we're having E to be equal to 2.55 times 10 to the power 5 Newton per coulomb. So electric field is measured in Newton per coulomb. So the SI unit is Newton per coulomb since it is force over charge. So force is Newton, then charge is coulomb. So we take note of the SI unit as well. Now let's look at a second question. Two charged spheres, 4 microcoulomb and minus 3 microcoulomb, are placed 0.9 meters apart. Find the electric field at the midpoint between the charges. So two charges, they are found at a distance of 0.9 separating them. And you are supposed to find the electric field at the midpoint between the charges. So we are supposed to find the electric field that's found between the charges at the midpoint. So into our solution, we are supposed to write two electric field equations since we are having two charges at this time. So we will get two electric field equations. So E1 will be for charge 1, then E2 will be for charge 2. So the general equation that we know for electric field, we specify each for each charge. After that, we write out our parameters. So Q1, Q2, then here our R will be 0.9 over 2. Since the electric field you are finding is at the midpoint between the charges, so we find the R to be 0.9 by 2. Then we know our K constant. So therefore we take them one after the other. Then we do our substitution. So for E1, we are having 8.99 times 10 to the power 9 multiplying the fraction 4 times 10 to the power minus 6 all over 0.45 squared. And we are getting 1.78 times 10 to the power 5 Newton per coulomb for E1. Then E2, same substitution, K multiplying the fraction 3 times 10 to the power minus 6 over the same distance 0.45 and after computing, we are having 1.33 times 10 to the power 5 Newton per Coulomb. So after these, you're supposed to find the total electric field at P from both charges. So we combine them, or we sum them up. So we're having EP, which is electric field at P, equals E1 plus E2. So EP will be equal to 1.78 times 10 to the power 5 plus 1.33 times 10 to the power 5. So after summing them up, total electric field found at point P is 3.11 times 10 to the power 5 Newton per Coulomb. So this is the step by which we go through in finding an electric field at the midpoint between two charges. So here is a trial question. Pause the video and solve the question to get the answer.